Let's take a look at Q3 from section 3.2. In this example, I'm giving you sort of the shortest question that I'll ask here, which is just find the general solution, or graph the phase plane, not giving you much. Very importantly, I've given you a second order single differential equation rather than a system of linear differential equations. So what we're going to need to do first, we need to convert to a system and find the coefficient matrix associated with that system. Once we've done that, we can find our eigenvalues. Once we know the eigenvalues, we can use them to find our eigenvectors. Once we know both the eigenvalues and the eigenvectors, we can do two different things. One, we can state our general solution. Two, we can draw a graph of the system. These two are not really dependent on each other. These two are both dependent on us knowing both the eigenvalues and the eigenvectors right here. So we'll do this in a series of steps. First thing we need to do is we need to rewrite our second order differential equation as a system of first order linear differential equations, and then extract the coefficients to determine what is the A matrix we're looking to work with here. So we're going to do the same steps that we always do here. We know that we're looking to talk about a sequence of two derivatives on x, so we'd like to define variables for one at a time. Even though it's not always the case, I always like to think in terms of position, velocity, acceleration here. That's always where I go to in my head, whether this is a physics problem or not. I like to think to myself here, this should be a velocity term, and that's an acceleration term. So if I'm trying to really describe position, then the first thing I should say is that the derivative of position over time is velocity. I can then say that the derivative of velocity over time, well, the derivative of velocity is acceleration. Acceleration is the same thing as the second derivative of position. And so I think that just by solving for x double prime, I have also solved for dv dt. These two terms are the same as each other. So I'm going to go ahead and subtract both of these terms to the other side to get my expression that goes here. Notice that x prime is the same thing as v. So I'm going to write this as negative 10x minus 7v as my statement for dv dt. By the way, one other thing I'd like to say here is typically if I were in regular algebra land, I would probably subtract these two over to the other side, keeping their ordering right here. But to me, it's really important that I kind of keep my first variable first and my second variable second. I almost don't like the fact that I wrote the v right there, because to me, v belongs in the second slot associated with this equation. You should always order your variables in a consistent way, because the whole point is we're trying to extract off their coefficients in order to come up with our A matrix, so the ordering really does matter here. We should see that this is going to take us to the A matrix of my coefficient on x here is 0, my coefficient on v here is 1, coefficient on x is negative 10, coefficient on v is negative 7. So now that we know the A matrix that we're interested in working with here, let's go ahead and use that to find our eigenvectors, find our eigenvalues, then find our eigenvectors, use those two parts to come up with all the information we want to know about this problem. So now we can go ahead and find the eigenvalues in the usual way. Remember that we're always interested in solving the equation determinant of A minus lambda I equals 0 to find our eigenvalues here. So I'm going to take the determinant of negative lambda 1, negative 10, negative 7 minus lambda, and I'm going to set this guy equal to 0. In this case, again, with my factoring out some negatives trick, it looks like this should just be lambda times lambda plus 7 minus negative 10 in this case. Be careful here. This is typically like the type of warning I give to my algebra and trig students. But man, I don't care how much algebra you've done, I know a ton of people are going to drop that negative here at some point. So recognize that this is AD minus BC. Here BC was negative, we're subtracting a negative, that should be an addition. Now there's another hint though that goes with this as to how we know where we're getting at here. I am hoping that everybody has the visual awareness to recognize that this statement right here seems to me to be just the literal exact same thing as this, except for rather than polynomial type action, we're doing derivative type action here. But this is no coincidence right here. All of section 3.6, I think it is, either 3.6 or 3.7, is basically just going to say, oh hey, hopefully you've noticed this relationship by now, so how easy is that? So by the way, I certainly expect it to be the case that in a couple of weeks, if I say to you, tell me the eigenvalues of this system, you can literally just look at it and say, negative 2 and negative 5. Because all that is just factoring a quadratic right there. And that's exactly what we see right here. Lambda plus 2, lambda plus 5. And it looks like we found lambda 1 is 2, lambda 2 is going to be 5. So we found our -2 and -5. We found our two eigenvalues. Let's now go ahead and use those two eigenvalues to find our eigenvectors. So we've seen that our A matrix is going to be 0, 1, -10, -7. We've computed that our eigenvalues are going to be -2 and -5. We'd now like to use each of the eigenvalues to come up with its corresponding eigenvector. We want to remember that we're still using our AV equals lambda V equation, slightly modified here. We've grouped up together some terms so we can help ourselves solve for V here. So we're going to compute what is A minus lambda I using this lambda and solve for the associated eigenvector V. We'll do that for both cases here. In our first case, A minus lambda I, 0 minus lambda in this case is +2, 0 minus -2. We keep the 1 and the -10 on the off diagonals, and then -7 minus -2 should be -5. I'll multiply this by a generic UV vector to get our 0, 0. And hopefully in this case right here, I think we can kind of visually see what we need here. It looks like if again, I typically like to choose 1, especially for U, if I can. And it looks to me in this case, if I've got, and notice here, this is just the equation 2U plus 1V equals 0 is the equation that I'm working with here. So it looks like if I let U be +1 and V be -2, then we'll go to 0. Again, I'd like to point out, these two are redundant. These are equivalent pieces of information right here. There's no help that I get from looking at the second row relative to looking at the first row. They're the same. I just looked at the first row because it was easier numbers than the second row right there. With these redundant pieces of information, that suggests to us that there should be a whole line of solutions, not just one solution. Any constant multiple of this is also an acceptable answer here for V1. Finding V2, we can do the same thing. 0 minus -5 is +5. Off diagonals remain. -7 minus -5 is -2. Again, by doing a little bit of visual inspection here, it looks like I can let my U be a +1, so I have 5 so far. In that case, I need a -5 to cancel it. So if I let V be -5, then 1 times -5 is my perfect cancellation term right there. So it looks like 1, -5 is my simplest result that I can state for my second eigenvector. For those of you that might be identifying some other patterns that we're not going to formally talk about until section 3.6 or 3.7 or whenever we talk about our second orders out there, another thing that you should notice that just happened right here, and this will happen in all of our second order systems right here, is that our top value on each of our eigenvectors was 1. Our bottom value on each of our eigenvectors was actually the eigenvalue itself. That'll be a pattern that we'll more formally identify. I don't think it's too terrible to just identify that by visual inspection, or if you need, write those equations for yourself for helping determine what should your eigenvector be. This is one of those things that I never write out by hand and haven't for years, but I know that I used to, and so until you get used to actually looking at these things and kind of seeing it for yourself, it's fine for you to write a little equation and say to yourself, what values could U and V take on to make this true right here? There should always be an infinite number of solutions. You're always looking to state a simplest possible solution for yourself just so that you have easy numbers to work with. Now we found our A matrix. We used the A matrix to find the lambdas. We used the lambdas to find the eigenvectors. Now we know the eigenvalues, the eigenvectors. That should be all the information that we need to do things like state our general solution and draw our graph. Let's go ahead and state this general solution first, then we'll draw a graph. What we've seen is that our general solutions are always going to be of the form y of t equals. We're always going to get a couple of constant multiples. Given some initial conditions, we could solve for these k1s and k2s. Our results are always going to have these exponentials in them. That's the only way we're really going to find solutions to these things, with the exception of trig functions, which we're going to see next week. We're always going to find that our lambdas end up being the coefficients on our powers here. So here I'm going to state this as lambda 1t v1. And we just get another grouping of this over here. Another thing that you should notice real quick is that this is our linear combinations of our two simple solutions right here. Our two small solutions are the EV parts. By finding all sums and differences of constant multiples, we've found all linear combinations of the two solutions that we've found here. In our case, this is going to look like k1 e to the negative 2t. Which vector goes along with e to the negative 2t? The 1, negative 2 vector. We also have the terms k2 e to the negative 5t. Which vector corresponds with the eigenvalue of negative 5? 1, negative 5. This would be the most general way to state this. I'm going to write 2 other lines here just so that you can kind of see some other notational things, but this is kind of the general format that I'm hoping to see in the future from you, but we need to understand it, which is why I'm going to write it a couple different ways real quick. One thing I could do is I could go ahead and multiply this thing out. What this thing is going to look like to me is k1 e to the negative 2t. We had 1 copy of that on top. We have negative 2 copies of it on bottom. We are adding that to 1 copy of k2 e to the negative 5t on top, and negative 5 copies of it on bottom. Finally, what I might say then is that this is really our y of t, but remember that this is the same thing as just x of t, v of t. And so notice here that if I were really, so I guess what we have to do right now, since we haven't formally talked about solving second orders, is we shouldn't just be stating solutions just for x. Since we created a new variable of v, then we should track that variable of v, the derivative of x. So we've given our solutions for both parts here. But you should notice that later in this chapter, when I just say give me the solution for this, I really just want to know what formula do we get for x. And you should recognize that we've got exactly that formula here. So there is our x of t solution to this differential equation right there. The other thing I'd like you to notice, why did we get that this was 1 and that this was lambda? This was 1 and that this was lambda right here. Well, what's the relationship between x and v? V is just the derivative of x. And so if I take the derivative of e to the negative 2t, what happens? Well, a negative 2 pops out. If I take the derivative of e to the negative 5t, a negative 5 pops out. So it really shouldn't be too terribly surprising here that we get this relationship. This is sort of saying to me, if your coefficient was 1, then after a derivative, your coefficient is negative 2. Or any constant multiples of that exact kind of scenario right there. What constant multiples? Well, we have constants built in to handle these, k1s and k2s. So kind of what I hope to see happen here for you guys is that there should be like 40 ideas that are like converging for you to realize that they're actually one idea. And I think that's kind of the hardest part about the beginning of this chapter, is recognizing that we're really just doing the same thing over and over, like 12 different ways. And it's really important that we kind of realize why these are all happening, why they're all equivalent to each other. Now that we've stated a solution, I'm not going to use the solution for my graph, but I do want to again use my eigenvalues, eigenvectors to go ahead and draw a quick phase plane. So to wrap up this example here, we just want to try and graph a quick sketch of our phase plane. I'm going to use a slightly different technique than I used the last time to kind of fill in all the parts here, but we're still going to start with the very, very important same beginning steps right here. What I want to identify is that what we've done by finding eigenvalues and eigenvectors is we've found the 2 straight line solutions that we are hoping to find. What we found is that one straight line solution lives on the line that's equivalent to this vector, 1, negative 2. So I can go 1, negative 2. See that we're really looking at just a line of slope negative 2. And so there is one of my straight line solutions. The next vector is going to be the, oh sorry, I should label this before I move on here. This is my v1. For my next vector, 1, negative 5, I should be able to go 1, negative 5 down here. It looks like this is just going to be a slope of negative 5 line. Unfortunately, slopes of negative 2 and negative 5 are not that far apart graphically right there. So those look to be my 2 straight line solutions. I know where my straight line solutions are, but now the question is, what's actually the action on that straight line? Well, both of my eigenvalues here are negative, and so I am expecting to see decay happening along both those lines. That is, we should be experiencing sink type behavior along each of these straight line solutions here, since both eigenvalues are negative. So I'm going to go ahead and put my arrows on. Now, this is a really good start. I think that these are the two most important solutions in this entire phase plane out here. Out of the infinite number of initial conditions, I think we've talked about two sets of them that are the most important, are straight line solutions. But what I don't know is what the rest of this phase plan looks like. Now, what we could do is we could talk about the discussion from our Q3, or Q2, sorry, I didn't change that. We're on Q3 right now. But I think there's a little bit of an easier way right here. One of the things that I think is typically pretty easy for myself is to think about what's the behavior on the axes. In particular here, I'm going to go ahead and look at the x-axis. The x-axis is, x-axis, and here, unfortunately named, we have the v-axis, right? That's our velocity, not to be confused with that v, which stands for vector right there. So remember that we have x and v as our two variables here. And so what I know is that from our original system, dx dt equals v, dv dt equals negative 10x minus 7v. What I want to see here is what happens if we just let v be equal to 0. If v is equal to 0, then that just says, what's the action on the x-axis? Well, in this case, it looks like we're going to get dx dt equals 0, which means we're not moving left or right at all, which means we're only moving vertically. What direction are we going to be moving vertically? Well, dv dt here, it looks like, if v is 0, is going to be negative 10x. So what this says to me is this: if x is positive and v is 0, then we're on the positive x-axis. That says don't go left or right at all, but if x is positive, we should be heading down. Negative 10 is our dv dt value. So I'm seeing that anywhere that we're on the x-axis, the positive x-axis, our direction should be straight down. And the further out we go, the stronger those vectors are. Those should be getting bigger and bigger in a sense as we move further away. I just never draw the right sizes. If we're on the left side of the axis over here, then v is still 0. We're still not going to move left or right at all. But now that x is negative, our dv dt is positive. So we're only going to go straight up right here. So now I just have to convince myself of what all the rest of these trajectories look like. What I know, based on my two eigenvalues of negative 2 and negative 5, is that if all solutions in the phase plane can be constructed as linear combinations of these guys, then we're always experiencing decay. There is no route that I have to experiencing growth. Our two full descriptors of our scenario both give me decaying information right here. So everything is certainly going to decay towards the origin right here. The question is just, what path is it going to take? Well, what I can kind of picture for myself here is if I start a point, maybe in the third quadrant out here, what I know is going to have to happen is, one, I'm going to stay in this region over here. I've got these walls of my solutions that I can't cross. And I know that I have to cross the x-axis only going straight up. Finally, I know that where this point will eventually end up is at the origin, just like all points will as time goes off to infinity. So I'm picturing our remaining trajectories looking something like this. Those are just two of them, but you'll be able to find that there's, a whole family that look essentially the same as this idea right here. When you graph this in p-plane, which you should. You should also, I think I posted a link in the Discord, at least, that should be pinned to the top for a in-browser version of phase plane. If you don't have p-plane, a phase plane grapher, you should definitely be graphing all these things with technology here. So look for that guy in browser, go to Discord and check that thing out. Other than that, I think this wraps up Q3 here, so let me know if you have any other questions about this thing.